Hello, I hope my voice is audible. Good afternoon, everyone. Today is the live session for the course entitled as Introduction to Photonics, and we are here to solve uh, some problems and along with the discussion which will be for the week 4 classes. So we'll wait for some time, and after that we'll start today's live session where we'll discuss a few topics about the week 4 classes, and we'll go for the question answer session. So please wait for some time. Okay, so let's get start. Uh, we will discuss a few short details about the week 4D course. So we'll start from the quantum blueprint of light. So as we know that we have already discussed in the previous 3 weeks about the uh, ray nature of light, wave nature of light, and electromagnetic wave nature of light. Now we are discussing about the photonic level, the quantum level nature of light. So to master this interaction of light and matter from single photon to optical amplification, we are going to discuss in this. So the photon more than just a particle, as we know that the photon is not just a wave, not just a particle, it shows the wave particle dual nature. So as we discuss about the energy, we will discuss in terms of the quanta, and the quanta energy is defined as E is equal to h nu, where the wave particle duality, a short pulse of 100 femtosecond, inherently carries a massive spectral width of 10 to the power 15 hertz. So you can see here that in the few millisecond the frequency hertz how much it is, spectral massive bandwidth. Then the spin angular momentum also we have discussed that the spin angular momentum is S is equal to plus minus h cut, represents left or right circular polarized light. And talking about the orbital angular momentum, then it becomes the L is equal to L h cut, and this L h cut is this defines the photons can travel in a helical path. You can see here how the helical path is defined here, and that depends on the positioning of phase singularity at the center, null intensity at the center. You can see here that the phase singularity, null intensity on the center. If you are talking about the quantum nature of the light, so where the first rule comes of the transition, where the excitation happens in the atom, and the excitation photon takes the electron to the excited state level, and there the process happens of non-radiative decay process happens, that is relaxation, and it doesn't generate any kind of radiation. But moving towards the emission part, what happens there, that excited state atom's electron goes to the ground state, where it generates the low energy photon, higher wavelength photon, which is E is equal to h nu emission. So the photon is mentioned here as h nu emission. So the energy filters, so on this basis we can define it in a different way. It's like a red light passes through the entirely undetected because its energy does not match with any energy gap. So red light will not, neither it will be excited, neither it can't excite the atom, neither it can be emit. So here we are taking a best example of rhodamin 60, where it is absorbing the green light and generating the orange emission. Measuring the quantum stream. If you are talking about the macroscopic view, the CW laser looks like a very shiny and bright light. But if you are talking about the 1 nanowatt power at 200 nanometer wavelength, so what we need to see that photon flux density, and that depends on the power divided by the h nu, photon energy. So the power is here 1 nanowatt, and the frequency we can calculate using the lambda value even. So according to this, the photon flux density comes as 10 to the power 9 photons per second. It means that each 1 second each 1 nanosecond, one individual photons are arriving to the detector. So this in this continuous stream energy, we are receiving exactly one individual photon at 1 nanosecond. So that's what the photon flux density determines us. And talking about the high photon density laser cataract surgery. So what if we use the CW laser? Why we need to go for the femtosecond laser? So depends on depends on the thermal dissipation or thermal carrying and collateral damage. So CW laser continuously hits the photons to the skin tissue, and those tissues, because the light is continuous, each and every photon will generate the high massive energy, which can be converted into thermal energy, and that can rupture the tissue. While talking about the pulse laser, suppose the 1064 nanometer pulse laser with 100 femtosecond pulses, what happens is the photon density is 10 to the power 19 photons square, photons per second centimeter square per centimeter square. It means that the packed into a femtosecond time scale, and if you are talking about this femtosecond time scale, in 100 femtosecond there will be 10 to the power 19 photons will be arrived at per centimeter square area. So it means that a huge pulse is coming to the at a one time, like a bullet gun, and instead of rupturing the tissue and generating the localized energy, heat energy, it will just dissipate once it is changing the it's doing the it's laser cataract surgery, and the result will be the precise micro incision photo disruption with zero thermal buildup. So each pulse, after 100 pulses, 100 femtosecond pulse, it may be a delay of some few millisecond. So each pulse will be having enough time which can prevent the heat generation in the tissue. Talking about the poisonous nature of the light, if you are talking about the 10 GB per second optical telecommunication signal is propagating, where you have the transmitter and receiver, and transmitter is generating 10 GB per second optical signal, and detector is detecting it. So the targets and the mean of the mean number of photons are 20 per 1 bit. So here it should be 20, here it should be 0, here it should be 20. But the quantum reality is spontaneous emission is probabilistic. Arrival follows a Poisson distribution. So the error rate, sometimes what happens that there will be a error rate if you are getting a non-photon which should be come into the 1-bit binary. So for that, even with an average of 20 photons, there is a 2 into 10 to the power 9 minus 9 probability of the exact 0 photon arriving in a slot, causing a bit error. So how light and the matter engage? Absorption. Talking about the absorption, then spontaneous emission also we have discussed just now. The emission which is coming instantaneously, but it is having some lifetime. So decay after characteristics lifetime, that is del SP. So it generates the longer wavelength photon. And then coming to the stimulated emission, emitted photon is perfect clone, exact phase, frequency and direction, which is called stimulated emission. This is very useful for the lasing action. So if you are talking about the quantum if you are balancing the quantum laser of the absorption rate and the emission rate, and if you are considering the stimulated emission is um, overcoming the spontaneous emission, so what happens that the equation which is that b dash n1 is the number of photons which are absorbed by the material, and PEM is the probability of the emission, and there is equation which is a n2 for spontaneous and b n2 PEM for the stimulated. This should be PEX. So this PEX and PEM, if it is if we consider both are same, so what will happen? So under first we'll talk about this one. Under steady state condition, the transition up equal transition down, Einstein matches this exact equilibrium to Planck's blackbody radiation formula. So the environment dictates the rule. So here, if you're talking about the dilution of the gas, example rhodamin 6Z, the statistic Boltzmann distribution statistics based on the Boltzmann distribution and the absorption profile shows that the discrete specific energy transition. As you can see here, that the excitation discrete absorption will go to the E2 of the another fingerprints, and it will generate the stimulated emission. Talking about the semiconductors, statistic Fermi direct distribution absorption profile, continuous absorption everywhere above the band gap energy threshold. Continuous absorption above the band gap. This is the band gap. So in the semiconductor, in the dilute gas or the organic material, this will be Boltzmann distribution, while in semiconductor it will be Fermi Dirac distribution, and absorption profile will be continuous absorption everywhere above the band gap threshold. Talking about the thermal equilibrium, and which is incoherent light, so highly random emitting zero photons at a even instant is mathematically more probable than the emitting n photons. So the thermal light will be incandescent light for Bose-Einstein. While talking about the engineered light, which is laser, or we can say the Poisson's light, so here highly coherent peak around a high mean number of photons. So there are number of photons will be higher here compared to here, and here it is the number of photons, and the probability has been discussed here. So the thermal light is dominated entirely by spontaneous emission. The result is statistical chaos. And talking about the limits of the thermal equilibrium, when we are talking about the temperature, if you are increasing the temperature, then N1 ground state energy will be higher. Optical radiation engineering, this is the thermal energy at the room temperature 25.6 milli electron volt, and optical radiation energy is h nu is equal to 1 electron volt. So N1 is ground state, N2 is excited state, and this is an invisible velocity. The iron law of equilibrium. Boltzmann's law dictates that under pure thermal equilibrium, the higher energy level N2 will always hold fewer atoms than the lower level N1. Spontaneous emission will be always same. This is the Boltzmann's law dictates. Now the breaking the rule. Usually if we are talking about that ground state energy in ground state number of atoms will be number of atoms, which is n1 at ground state, will be higher than the compared to the atoms at the excited state n2 at higher temperature also. But while breaking the rule, the population inversion, is it possible to get the excited state number of atoms at the excited state compared to the ground state? So the natural state, this is the phenomena. But if you are talking about the external optical and electrical pumping, it can be possible to do opposite to it, which is higher number of atoms at the excited state compared to the ground state. And this, to achieve optical gain, we must operate this outside thermal equilibrium. We must force the system into a state where stimulated emission has been statical advantage from single clone to laser beam. If you see here, the n2 is greater than n1, and then that's why the each photons will take another photon from the releases, because one atom will be goes to the ground state, and both generates these two photons, and each photons again generates the double of that, and another multiplication happens. When n2 is greater than n1, the probability of the stimulated emission overtakes spontaneous emission. This runaway cloning process is the mechanical engineer of the laser. Mechanical engineering engine of the laser. So the physics of the optical control. So the photon, understanding wave particle duality and angular momentum, goes to the static knows for the phase 2, which is statistics, using Poisson's distribution to measure discrete photon flux and pulse density. Then the interaction, defining the mechanics of absorption, spontaneous emission and stimulated emission. And then the last one is the amplification, defeating thermal equilibrium through external pumping to achieve population inversion. We have transitioned from observing the chaotic statistics of natural black bodies to the particle quantum engineering to coherent light. And in the end, we are talking about here the uncharted frontiers of light, where the Einstein coefficient of nonlinear media, Poisson's limit in the 100 G plus telecom, and the femtosecond ablation mechanics. So we have defined the quantum blueprint, the application of the discrete packet, whether this precise surgical photo disruption, error-free telecommunication, or structured vortex beam, is the future of the optical engineering. Floor open for discussion. Thank you. Now talking about the question answer session. So we'll wait for 5-10 minutes and we'll start the question answer session here. Okay, so let's discuss about the question answers. A continuous wave, a CW laser emits 1.55 micrometer radiation at a power of 2 milliwatt. Calculate the approximate photon flux arriving at a detector. Could you try to calculate it? We know that the phi is nothing but the P divided by H nu. If we give the power 2 milliwatt, H Planck constant, and the new value mu can be multiplied here 1.55 micrometer, then Hc if you can keep, and it can be calculated. So so if we can keep in this way, maybe energy, this is the energy actually, so energy can be calculated using the equation which is E is equal to 1.24 divided by lambda, and based on that we'll get the energy value 0.8 electron volt, and which means it will be we need to convert it into joule, and that will be 1.28 into 10 to the power minus 19 joule. And if you are dividing the 2 milliwatt, which is power, by this energy yield, which is 1.28 into 10 to the power minus 19 joule, so we'll get the correct answer here. Watt we can convert into milliwatt, we can convert into watt, so watt is nothing but just joule per second. So if we cancel this and if we calculate this, the value will come approximately 1.56 into 10 to the power 16 photons per second. Okay, so the calculate approximate flux density they are asking, so the phi will be approximately this much. Moving towards the next question. In an optical communication system using Poisson's arrival statistic, What is the probability of a bit error occurring due to 0 photon being detected in a one slot where the mean photon count n bar is 15? Could you try to answer this? Is it possible? So it's a very simple question. We need to define, or we need to know about the probability of the bit error occurring at the 0 photons detected at 1 bit. So it's possible we can say that P probability of finding 0 photons is at 1 is exp minus n bar. What does it mean? Which means n bar is 15 equals, so the P naught or P0 becomes 3 into 0.59 into 10 to the power minus 7. This is the correct answer. Okay, the next question is, an atomic system is thermal equilibrium at room temperature which is kBT is equal to 25.6 milli electron volt, has two energy levels separated by 0.5 electron volt. What is the ratio of the population in the excited state to the ground state, N2 by N1? So it's basically the energy has been given of two level, the energy gap has been given between the two levels, asking for the ratio of the population N2 by N1. Could you try to answer this? N2 divided by N1, it is Boltzmann distribution equation is exp minus del E divided by kBT. What does it mean by? So as we know that exp del E is given, the energy gap between two energy levels are given as 0.5 electron volt. So in milli electron volt it will be 500 milli electron volt. And if you are talking about the kBT value, that is 25.6 milli electron volt. And after keeping these values and solving this, the ratio of n2 by n1 becomes 3 into 10 to the power minus 9, which means the n1 population is 2 way higher compared to the n2 excited state. If this is the n1 and this one is n2, so here you can see the energy gap, which is 500 or 0.5 electron volt at thermal room temperature. The ratio of this two will be 1:3 into 10 to the power 9. Not 10 to the power 9. So it will be 3.3 10 to the power 9 ratio, 10 to the power 8 ratio. Okay, so this is the ratio. There will be n number of electrons here, this many numbers of electron, and there will be one electron in the excited state. This is the probability of that population ratio, and you can see that the ratio will be 3. The n2 by n1 will be 3 into 10 to the power 9 minus 9. Okay, so the correct answer is this one. Now the next question: if a pulse laser produces a pulse duration of del t is equal to 200 femtosecond, what is the approximate minimum uncertainty in the frequency del nu of the light? As we know that del t and del nu should be equal to approximately 1. According to the uncertainty principle, the frequency spread is the inverse to the pulse duration. So if you are talking about the pulse, which is 200, del t is 200 femtosecond, then the approximate minimum uncertainty of the frequency will be del nu, and both will be, usually it will be like this: del t is 1 by del nu. So approximately, so it means that the del nu we need to find out, and it will be easily we can find out, which is del nu is equal to 1 by del t, which is 200 10 to the power minus 15 second. So it will be 200.5 into 10 to the power 13 plus 13, and which means 5 into 10 to the power 13 hertz per second actually. Second number. So this will be the correct answer here, option D. So the approximate minimum uncertainty in the frequency del nu will be in the light is this one. Next question: A metastable state population N2 decays spontaneously if the spontaneous lifetime del TSP is 10 nanosecond. How much time is required to population to drop to 10% of the initial value N2 naught? Try to answer this. So the correct answer here will be at time t n2 we need to find out what could be how much time we need to find out the n time t n2 t. So n2 t no the time we need to find out. So for that n2 t at the time the n2 will be n2 at initial time e to the power exp 1 minus t divided by tsp. So at setting the value n2 naught which is 0.1, it means like the n2 drops to the 10%, so it means 0.1 is equal to this value is 0.1, so is equal to this value n2 naught we need to find out. For that we knew that the n2 naught is here 100%, so 1 exp minus t we need to find out, and we know that tsp is 10 nanosecond. So after keeping all these values we'll get approximately 10 ln 10, which is 23 approximately 23 nanosecond. So this is the correct answer for this option number A. Okay, so So the next question, why is the stimulated emission process often described as producing a clone of the incoming photon? What could be the reason for this? The reason is quite simple. The clone means it has same phase, same frequency and direction as well. So that's why it is called a clone photon. The emitted photon shares the same phase, frequency and direction as the incident photon. Now calculate the next question. Calculate the signal to noise ratio SNR for an optical detector measuring a photon stream with a mean count n bar, which is 100 per measurement interval, assuming Poisson statistics. So as we know that the Poisson statistics is n square is equal to sigma square is equal to n bar, which means the SNR is where making the SNR n square sigma square, it means n square divided by n bar square divided by n bar, which is n bar. So if we have the signal to noise ratio in an optical detector measurement, a photon stream with a mean count of 100 per measurement interval, assume the Poisson statistics, this will be the SNR. So the correct answer is 100 only. Why not 10? Because 10 is the square root of the mean representing the standard deviation. Also, and 1 also not possible because the NSNR of 1 would be imply the signal power is equal to the noise power, which happens only when the mean count is 100. Mean count is 1. Moving towards the next question, which is which probability distribution must be used to describe the occupancy of energy level in a semiconductor material with overlapping wave functions? So as we discussed previously that gas phase or an organic system, the distribution will be Bose-Einstein. Here we have discussed already. Boltzmann distribution, and in semiconductors the Fermi-Dirac distribution. So this semiconductor thing, this will be defined in the Fermi-Dirac distribution. Next question is, a surgical laser pulse with 1 joule of energy is focused onto an area of 1 mm square. What is the energy density in the unit required for tissue ablation? 1 joule per centimeter square. So energy density in unit required for tissue ablation we need to discuss. Since as we know that as we know that 1 joule concentration is in 100 mm square, which is 1 centimeter square. So 1 mm square, how much it will be? So it will be divided by the so we need to see like this. J, you need to check the energy density. So energy density in required tissue ablation. So we need to calculate the energy density ED. For example, I am writing here. So 1 joule, it is in 100 mm square. So we need to count in 1 mm square. It means this will go here, so it will be 100 joule. Per centimeter square. So it will be 100 joules per centimeter square. Moving towards the next question, which is a photon is characterized as having a charge L is equal to 3. What is the orbital angular momentum? As we know that orbital angular momentum is L h cut. So it's a 3 h cut. So correct answer is this one. Now talking about the under thermal equilibrium condition for optical radiation, why is spontaneous emission typically far more portable than the stimulated emission? Because the correct answer is here, this one, because the thermal emission, which is kBT, is too low compared to the photon energy, and that's why the population inversion doesn't happen, and that's why we are not getting any stimulated emission where the spontaneous emission dominates. So option B is the correct answer here. Now talking about the next question, in the context of Rhodaman 60 dye experiment, why does green light produce orange emission rather than red light producing orange emission? Option A, higher orange light has higher frequency than green light. This is not making any sense. Red light would result in blue slit emission while the human eye cannot see, which is not possible. The dye molecule only reflects red light, preventing any internal energy transfer. And the last one is green photon have sufficient energy to reach the excitation level while red photon do not. This is the correct answer. The dye molecule only reflect light. Reflection happens when the any medium is having the reflective coating. This is like mostly the transparent for this particular dye. So that's why this is preventing an internal energy transfer. So correct answer is option D. So we are in the last of the session. So as you can see here, that steady state condition is in rate equations imply that the rate of absorption and total emission are equal and populations do not change with time. There are zero atoms at the excited state N2. Spontaneous emission has been completely surpassed by stimulated emission. The laser has just been switched on and the power is rising rapidly. So these all are incorrect. This is not possible. Switching on power on rising rapidly. So this is population inversion takes time. Then spontaneous emission has not been completely surpassed by stimulated emission, which is also not possible because steady state condition shows stimulated emission surpassed by the spontaneous emission. There are zero atom in the excited state, not possible. If it is a room temperature also, few atoms will be there in the excited state. The rate of the absorption and the total emission are equal and the population do not change with time. That is the correct answer. Yeah. So the steady state means the system has reached equilibrium where the rate of the atoms going up equals to the rate of the atoms going down. The specific condition has spontaneous emission probability density PSP, which is equal to 5.5 into 10 to the power 7 per second. What is the spontaneous lifetime? PSP is given, we need to consider the lifetime. So as you know that the lifetime TSP is nothing but the 1 by 5 PSP. So it will be 1 divided by 10 to the power 1 divided by 5 into 10 to the power 7, which means 0.2 into 10 to the power minus 7 second, which means 20 into 10 to the power minus 8 second, which means 9 second, which means 20 nanosecond. So the last question, true or false? To 20 nanosecond. This is the correct answer. Last question, true or false? Thermal light source like incandescent lamp exhibit a flat photon distribution because individual emission events are statically independent. So what could be the correct answer here? The correct answer will be because the incandescent light exhibit a flat photon distribution because individual emission events are statically independent. Yes, so this is the correct one. Why it is correct? Because it depends on the Bose-Einstein statistics, which means the large n bar results in the flatter, more random distribution. So you will be having more random distribution compared to the peak Poisson distribution in this way. So this is the way, and that's why this is true. The thermal light source depends on the Bose-Einstein statistics, and that's why it is a flat photon distribution. And here we'll stop today's live session. We'll meet next week and we'll continue for further next week's doubt solving and little bit discussion about the week 5